Okay, so good afternoon, everyone. I am Devadun Banerjee. I am going to sharing my screen in this live interaction session, number 5 of this particular NPTEL course, Technologies for Clean and Renewable Energy Production. I am a PMRF PhD scholar from Indian Institute of Technology, Delhi, and this course is will happen on 27th August 2023. So, what we do is we we do an overview of whatever have been taught you in this particular week. So we will go through the overview of the particular things and then try to address some sample questions so that your understanding would be more clear. So usually the overall thing has been taught is the gaseous fuels. So the gaseous fuel types have been taught. So what is a gaseous fuel? Which means that a certain gaseous substance which will be burning in air and releases enough heat or energy. So each and every gas will not be cannot be used as fuels. So that kind of particular gas which produces some amount of energy by combustion and releases enough heat, that would be called as a gaseous fuel. Okay, I'll just check this one. So the gaseous fuel types have been taught you. The what is the basically the advantage of these different gaseous fuels is the very much clean combustion, and you'll get a combustion efficiency or the energy efficiency is comparatively higher compared to the other types of fuel. The you can utilize different types of material synthesis like LPG or kerosene. So the end user convenience is also very nice. And obviously, the transportation, you will be requiring a very less amount of energy for transportation compared to the other types of fuel like solid or liquid. So the feasible transportation. So different types of gaseous fuels, what are there? Such as that which is available in nature. It's a natural gas, compressed natural gas, liquefied natural gas, coal bed methane, gas hydrates. These are the gaseous fuels which are available in nature. Then the gaseous fuel which can be produced from solid fuel, such as water gas, producer gas, coal gas, or syngas. And then what are produced from petroleum, like LPG, refinery gas, and the gaseous fuel produced by fermentation, such as biogas and landfill gas, like this. So these are basically a renewable thing. So in the fermentation process, what we do is we try to utilize some microbes or microbial organisms, and then this is a one of the kind of organic process. But the disadvantage of this particular fermentation process is usually a overall a biological process. So is kind of a slow process. So whatever catalyst or whatever reactant we are using, these are all organic. So maybe suppose some enzyme would be acting as a catalyst. So it's a biological catalyst. So however, the compared to the chemical catalyst, the reaction rate would be much lower for the biological process. Okay. Now the different compositions of the different gaseous fuels, what are they? Like the natural gas is having a 92% methane, 5% hydrocarbon, 3% inert. The LPG having a 20% propane or 80% butane combination. Now you can see that the due to the uh, higher carbon range, the typical heating value is much higher compared to the natural gas. On the contrary, again you go to the coal gas where the majority is the methane and hydrogen. Then the typical heating value is lesser than compared to the LPG, which is 20.2 megajoule per meter cube. Okay, and if you see the producer gas, if you see the syngas, the typical heating value is much lesser. So that is why LPG is used usually as a different as a fuel, basically the like the cooking and or maybe some other stuff also, right? So okay, so there are different quantities which can determine how is the property of a particular gaseous fuel. So the dimensionless density is one of such thing. Uh, uh, Okay, so the dimensionless density, which means that the density of the gas compared to density of air, which means that how much particular way would be there or dense would be there with this particular gaseous fuel compared to the normal air that it would be giving is a dimensionless density. It's different from the normal density. Normal density means is mass by volume. So, and for a particular unit volume, how much mass would be there for a particular gaseous fuel. That is important. That is actually provided by this dimensionless density. Then the UB number, the UB index is as this compared to the density, how much actually you are getting the energy from the gaseous fuel. So it is the is the ratio of the gross calorific value and the relative density to the power 0.5, where we consider the air is having a 1 density. Okay, so compared to the 1 air density, there is certain relative density of particular gaseous fuel, and then within compared to that density, how much we are getting the calorific value. So which means that mm, it would be indicating the interchangeability of the fuel gases such as natural gas, LPG, town gases, and is usually a very much important specification when we uh, actually define a particular gas thing. Okay. So if we this UB index, which means that the methane and propane having a different UB index, 55 methane, 78 propane. Okay. So if these UB index would have been same, such as methane and natural gas have very similar UB index, 55 and 50. So for a particular given pressure, for a particular valve settings, the energy output would also be same or very similar. Okay. That is the basically function of a UB index. So if you have particular combination or uh, composition of a particular mixed gas, so how much quantity how in how much ratio we are mixing our gas or the basically two different gases, that would be important. So that would be determined by this OB index. Then the temperature of dew point and moisture. This is also another important parameter. So in the compressor industry, the dew point is a very important measurement. The how much water content is in there. Okay, but the gas industry dew point is different. Is the hydrocarbon dew point? Is the it is what is it? It is the temperature at a particular pressure at which the hydrocarbon components of any hydrocarbon rich gas mixture such as natural gas will start to condense out of the gaseous phase. Okay, which means that the vapor portion would be decreasing. It would be getting started to condense. And for example, mm, if you take a certain gas, maybe CO2, okay? So at a normal temperature, CO2 is gaseous phase, but uh, normal temperature CO2 as a gaseous phase. Okay. Now, if you decrease the temperature, a certain portion of the CO2 gas would you'll see that it would be getting condensed. So that the first temperature when it starts to condense out of the gaseous phase, okay, that is called the this hydrocarbon dew point. Okay. The hydrocarbon dew point is a function of the gas composition as well as pressure. So when you talk about that, okay, there's whatever gas is there, uh, it is gaseous in this particular temperature. So you have to keep in mind that there is also a certain pressure. When it's a atmospheric condition, it is the pressure is also 1 atm. Okay, so it's the atmospheric pressure. So if you change the pressure, automatically the dew point will also be changing. Okay, because the vapor pressure and the other stuff will also get changed. Okay, so hydrocarbon above a certain molecular weight behave like any liquid, and they go back and forth between liquid and vapor. So after a certain molecular weight, basically the hydrocarbons will be similar behavior as a liquid. Okay, so there will be a liquid vapor equilibrium, and obviously this particular equilibrium composition will be depending on the temperature and pressure. That is why the hydrocarbon dew point is very important. Then the explosibility limit, such as before a fire or explosion can occur, three conditions must be met simultaneously. A fuel and oxygen must exist in a certain proportions, and then an ignition source should be there. Okay, so if a particular gas, such as uh, if we expose it in a temperature, if we expose it in air, and if there is a spark or flame, so there might be an explosion. So that limit we have to identify, because from the safety point of view, from the storage point of view, from the hazard point of view. Okay. So the ratio of fuel and oxygen that is required varies with each combustible gas or vapor. Okay. So what is the how do we define this particular explosive limit? Is the minimum concentration of a particular combustible gas or vapor necessary to support its combustion in air, defined as a lower explosive limit. Okay. So below this level, the mixture is too lean. So for example, for hydrogen, the lower explosive limit is 4, which means that the particular 4 percentage of concentration of the hydrogen should be there minimum in air, so that it can be combusted. Okay, below 4, maybe if you see that the 3%, so it might not be getting combusted, even if you give a spark, even if you expose it to air. Okay, similar thing is that the maximum level is called the upper explosive limit. Okay, even an important thing is that beyond this level, beyond 75% of hydrogen, the particular hydrogen air mixture it might be very rich. So it might happen that it might not also burn. Okay, so this range between 4 and 75 for hydrogen, maybe for methane is 5 and 15. Okay, uh, so that is why also the hydrogen is considered as a very hazardous gas, very uh, problematic gas due to this thing. Okay, so if you can see the range between the lower and upper explosive limit is very high compared to other hydrocarbons. Okay, there is methane shown, ethane shown, propane shown, butane shown. Okay, but this range you can see this between 4 and 75. So it's about 71% of range has been shown. Compared to methane, there is only 5 and 50. Ethane is 3 and 12 and 4. Okay, propane is 2 and 9.5, like that. And also the isobutene, propylene, propylene, all these things are shown. But the range for hydrogen is very high. That is why I have to be very careful when handling this. Yes. The next thing is the coal bed methane. Okay. So what is a coal bed methane? Is basically in some hard coal deposits, methane actually gets absorbed in coal under great pressure. So when it remains in the under this particular ground thing, uh, it experiences certain high pressure. So uh, under this high pressure, what happens is that this methane gets absorbed, and then what happens is when this particular pressure is uh, removed, because in the time of like excavation or the mining thing, so this pressure is removed, right? Then this the methane, the absorption of the absorbed methane would be dissolved, okay, and then we get the methane as a product. So the mine methane, you can see this about a very high rich methane, 96% methane is using. So this the during mining, the pressure in the coal field drops and the absorbed gases undergo desorption and revolve. Okay. So due to the processing applied the mine methane as a considerable content of air. So, obviously when this incoming air is in there when we are undergoing a mining. So about 20 to 50% air will also be there in this methane constituents. Okay. Then the application of this different gaseous fuel, that is also very important to understand. Okay. So, how these things can be actually applied? So, it can be applied for the heat and electricity production. It can be applied for liquid fuel and hydrogen production, uh, particularly via for as a liquid fuel such as methanol, such as ethanol, such as dimethyl ether. Okay, heterotron synthesis. This kind of reactions would be can be undergone. Then and actually overall, it how it can undergo is the natural gas. It is combusted to produce hot flow gas. Then a heat recovery unit. It recovers the heat, whatever constituent heat was there, and uh, uh, the electricity is generated form of the like the energy stored would be obtained via in the form of the electricity through gas or steam turbine. Okay. In the other route, what happens is that the natural gas undergoes a reforming reaction to produce syngas, which means the CO and hydrogen. The CO and H2 mixture is called the syngas, and then further cleaning, conditioning, synthesis. This particular steps would be there to form the liquid fuel, chemicals, or hydrogen. Okay. So, as I told also, it is can be applied for electricity production. So, how it can be applied for electricity production is that the CNG undergoes a combustion in the combustion chamber, and then it undergoes a gas turbine. Okay. Then it undergoes a gas turbine, and then from the gas turbine, it undergoes a compressing reaction in the compressor where the air is input, and this compressed air can be recycled to the combustion chamber, and then the further towards the alternator where we can get the electricity. And the turbine exhaust gas can also be utilized in the boiler, and then there is further steps in the condenser steam turbine, and again the electricity can be generated in the so the energy can be recovered in the form of electricity. So the next process, which is known as a reforming. So the reforming is actually a very important step for the natural gas utilization. So in the reforming process, natural gas is converted to the hydrogen and CO, which means that the syngas, the mix means of an exothermic or endothermic reaction, depending on the chemical process selected to perform the process. Okay. So in the usually is a catalytic process. The elimination of oxygen from the initial fuel mixture improves the overall system efficiently by minimizing energy losses from catalytic reactions. So, uh, methane undergoes a reforming reaction and it uses a C. So the product, whatever the product we are using, So the syngas will be other products. It can be used in the applications of steam, liquid fuel, chemical synthesis, all this kind of synthesis, or electricity generation, or heat generation, they can be utilized. So there are different types of for the steam methane reforming, partial oxidation, autothermal reforming, dry reforming of methane, combined reforming of methane, dry reforming of methane, membrane reforming. They are very important. So the top three, which means the steam reforming, uh, the partial oxidation, the autothermal reforming, they are very well established and they are widely employed by industry. Okay. The rest of the things, which are the dry reforming of methane, combined reforming, platform, they are actually usually innovative steps which are there to minimize the greenhouse gas emission, minimize energy consumption, and improve the reforming process yields. Okay, but they are in the Australian and asset stage, the research phase. Steam methane reforming, steam methane reforming, it is there are certain reactions such as SMR1. It's termed as an endothermic reaction where the methane undergoes reacts with the steam, produces syngas, CO and H2 mixture, CO plus 3H2. Okay, it's a endothermic reaction, which means that a certain amount of energy needs to be provided to make this particular reaction feasible. The other reaction is that methane plus 2H2O gives CO2 plus 4H2 is SMR2, which is it needs to provide a certain amount of energy. And the other reaction would be the water gas shift reaction, produced CO plus give us the CO2 plus H2, okay, to convert the CO, because CO is a very poisonous and toxic gas. This is a water gas shift reaction. This kind of different reactions undergo particular steam methane reforming. Okay. The typical temperature is about 700 to 850 degrees Celsius. The pressure is about 15 to 30 bar, and the hydrogen to CO ratio is about 3 to 5. Okay. Different types of catalysts can be utilized to reduce the energy requirement. The catalyst is particularly utilized, and the modern steam reforming catalyst uses nickel on a ceramic support with or without promoter stabilizer. Okay, the precious metals offer alternative to nickel. So nickel is usually a general catalyst. However, the precious metals can be a great help, but the cost is a thing. So for that purpose, extensive research is going to get a highly active, cheap catalyst. Because what calculation means such having high geometric area, high transfer coefficient, low pressure, obviously low carbon deposit to avoid the catalyst deactivation. Partial oxidation is another process. So how it happens is that a methane plus half O2, which means that oxidation, but partial oxidation gives CO plus 2 production syngas. So the if we give a complete oxidation, it would be producing CO2. Okay, so this is also a part of the two-stage process. As you can see that methane plus 2O2, it is producing a CO2 plus H2O, and then again it can undergo a further reaction to produce the CO plus H2O, so the synthase. So this is one two-stage process, or the direct step is the partial oxidation, which means CH4 less amount of oxygen. Uh, is half O2 less stoichiometric the from the complete conversion, complete oxidation, it would be providing a CO plus H2. in this particular highly exothermic process, and it is actually much faster than the steam reforming and requires a smaller reactor vessel. Okay, so the again it is producing the syngas. So that is very important. The first row of transition metals such as nickel, cobalt, precious metals such as ruthenium, rhodium, palladium, platinum, iridium. These are the very important catalysts in this particular oxidation reaction. The relative rates of carbon deposition would be in order of they will be catalyst that reduce the number of active sites, and this carbon deposition may even increase the pressure on the feed foul downstream processes. And the autothermal reforming is another process where it is basically a combination of the steam methane reforming and partial oxidation. Okay, so the it happens is the first step is the steam methane reforming, and methane plus steam gives the CO plus 3H2, and the partial oxidation methane plus half O2 gives CO plus H2. Okay, so the nickel based catalyst happens to be the best catalyst in this particular reaction. It's called as the autothermal reforming, and the temperature requirement in this particular process is 850 to 1000 degrees Celsius with under a pressure of 20 to 100 bar. The ATR reactor having a two zones as a combustion zone and the reforming zone. Combustion zone happens as the oxygen is given or air is given as a feed to combust the methane to produce CO2 and H2 and H2O mixture. The temperature is around 200 Kelvin, very high temperature. And then there is a reforming zone. So the reactions which are carried out in the reforming zone about 1200 and this is a methane plus H2O gives the CO plus 3H2. Methane plus CO2 gives the 2CO plus 2H2. Both of these are the endothermic reaction. But the first stage is the ectothermic reaction, which means that the first step when you perform, there will be certain energy released, a very high amount of energy will be actually released on the particular first stage, and then this released energy will be utilized in the second stage, is the in the reforming zone. So the by the proper adjustment of oxygen to carbon and steam to carbon ratio, the partial combustion in the thermal zone supplies the heat for completing the subsequent endothermic steam and CO2 reforming reactions. Okay, so the product gas composition at the exit of this particular reactor is just very close to the thermodynamic equilibrium of an adiabatic reactor, which means that a very high conversion will be getting. The next step is the dry reforming of methane, okay, where this methane plus CO2 gives us 2CO plus 2H2, and there is about it's an endothermic reaction at 247 kilojoule per mole is the delta H value, and nickel based catalyst commonly used. So there is particular no weight or the steam not required, where rather is a dry reforming of methane, okay, at a temperature of 630 to 850 degrees Celsius under a 1 to 20 bar. So the presence of the CO2 gives rise to more chances of carbon formation of catalytic surface. So here you can see the CO2 is also given as a feed instead of the steam. So CO2 plus methane. So you can actually directly convert both of these carbonaceous greenhouse gases, okay, to produce high value syngas. Okay, so the coke formation would be a very challenging thing to control it, or to be able to regenerate the catalyst will be very important. So the development of active catalytic materials, but with a very low coke formation rate, either on the catalysts or in the cold zones of the reactor, is a main challenge. The other process is the bi-reforming, where methane plus H2 gives CO plus 3H2. Uh, where there is the nickel-based catalysts are commonly used. But apart from that, the nanocomposites like nickel on zirconia support is superior to conventional nickel on zirconia nickel alumina catalysts in terms of the catalytic activity and stability. Okay, the usual reaction in the particular bi-reforming is happening to be the methane plus uh, H2O gives the CO and H3H2, again the syngas. Methane plus 2H2O gives the CO2 plus 4H2. Uh, CO plus H2O gives CO2 plus H2. Methane plus CO2 gives 2CO plus 2H2. Okay. Overall is an exothermic reaction and the H2CO ratio of 2, 700 to 950 degrees Celsius temperature and 10 to 30 bar. And as I studied about the bioreforming, the more combination of different processes is happening to be the dry reforming of methane. So it's the CO2 reforming, the steam reforming, the methane oxidation reaction, both the combination of this is called is the dry reforming. So the methane plus half O2 gives CO plus 2H2. The delta H0 is minus 35.6 kilojoule per mole. Methane plus CO2 gives 2CO plus 2H2. Is an endothermic reaction. The methane plus H2 gives CO plus 3H2. Uh, Methane plus 2O2 gives CO2 plus 2H2. This is again a very highly exothermic reaction. So the nickel-based catalyst, such as nickel, calcium oxide, zirconium, or nickel unsupported ceria and lanthanum oxide, or aluminum, quadrierite, uh, and even a nickel on ceria with a lanthanum doping. So these are all different types of catalysts which are very important for the spectrum hydrogenation reaction with the tri-reforming. So different reforming comparisons are shown here, that the steam reforming is having an very advantage of the heat recovery from the flue gas with a lower process temperature requirement. However, the endothermic reactions, it is having an endothermic reaction, which means that some energy has to be provided. Okay, instead of the feasibility is questionable. So the external energy requirement is there with the product gas as a H2 to CO ratio of 3, and the steam corrosion and the cost in handling the H2O, the excess H2O is also a challenge. Further, the partial oxidation, this is methane and O2 are the reforming reactant, where there is a no direct heat exchanger is required, and you can see the methane conversion is about a complete conversion, like the to 95 to 100% conversion of methane can be observed in this particular reaction. Further, it's overall a more compact than the steam reformer, and it's having a low reformer vessel cost. However, high cost of air separation unit and poor heat recovery are the disadvantages of this particular unit. The autothermal reforming having advantage of all heat needed is supplied by partial oxidation. Uh, Apart from that, the no direct heat exchanger is required, more compact than the steam reformer. High cost of air separation unit. Uh, Oxygen added lowers the hydrogen CO ratio in the product gas. The dry reforming having a lower conversion, however it having an advantage of the greenhouse gas, which means the CO2 is having used as a feed, which means the more amount of syngas along with apart from the methane can also actually convert it into the high value fuel or syngas. So the CO2 is the reactant. The specific ratio of methane, H2O and CO of 3 is to 2 is to 1 can produce a gas mixture with essentially 2 is to 1 ratio of hydrogen to CO2. The kind of reactor is particular quantity of linear reactor where a long parallel usually string channels there is a characteristic export happens on these particular walls and the physical properties of monolith. Physical properties of the monolith depends on the specific requirements of process. So the it is actually represented the cell density is represented the cell per square inch, which is nothing but the 1 by the diameter of the channel. So 1 by square of the diameter of the channel in inch. Okay, that is termed as the channel per the square inch. Okay, and the requirement, the advantages are like the good thermal conductivity for rapid heating of wash coat thermal expansion of same order of magnitude as the support. So when you talk about the uh, gaseous fuels, it is very important that in the particular first step is this methane is converted to the syngas as a gaseous fuel. The syngas wax and from diesel, which are formula upwards. So how they are basically regulated? The wax is hydrocarbon to diesel, the other products. Uh, Wherein the main reactions are CO plus 2H2 giving an hydrocarbon, the CO plus 2N plus 1 H2 giving a kind of a alkane, or so the paraffins is nothing but alkanes plus NH2O. The CO plus 2NH2 giving the olefins and then the Watergate shift reaction. Okay, so the CO plus H2 becomes CO2 plus H2. Okay. Overall, we are looking at a very highly exothermic reaction. Okay, which means that it would be released from this particular reaction. In the process, what it happens is the syngas is given the feed, the empty reactor is there, and then from the empty reactor, the wax is collected. Then the wax is hydrocracked to hydrogen feed, and this particular reaction product is transferred into the distillation unit, where we get different ranges of product from naphtha to kerosene and to empty diesel, Fischer-Tropsch jet fuel, and other Fischer-Tropsch products. And from that, the off gas is collected and they are actually combusted. Get the energy recovered. So from this particular things, it's important to understand. Uh, Liquid fuels can actually so the ethanol synthesis can be carried out technology for carbon dioxide and hydrogen is usually achieved over a copper zinc oxide catalyst. So copper oxide, zinc oxide, alumina. CZA catalysts are very important for this. CO plus 2H2 giving methanol. CO2 plus H2 gives CO plus H2O. And CO2 plus 3H2 giving methanol plus H2O. Okay. So different types of steps. So from the methanol and the to methanol synthesis, then overall exothermic reaction, and it's obviously favored as high pressure and low temperature. So the syngas feed is characterized by the R value is the H2CO2 divided by CO plus CO2. The desirable R value is around 2. So the what is the R value? It is nothing but H2 minus CO2, uh, and the ratio of this H2 minus CO2 at CO plus CO2. Due to the equilibrium constant, purpose CO conversion is limited to around 25%. The process operates at 220 to 250 degrees Celsius, uh, 5 to 8 megapascal, 50 to 80 uh, bar pressure. There's a particular reaction carried out, and it uses a series of catalytic adiabatic reactions. Okay. So generally a multi-tubular reactor, packed bed reactor recycle stream is employed from the methanol synthesis. And in the typical plant operation, the catalyst lifetime is about 2 years. However, the catalyst is very sensitive to sulfur poisoning, and therefore the sulfur level in fields where needs to be reduced. So usually in the industrial process, there is some high desulfurization unit is also placed before the particular actual reaction. Okay, to remove the sulfur, and it has to be removed up to uh, less than 0.5 ppm concentration. Catalyst deactivation also occurs due to thermal sintering of catalyst above 300 degrees Celsius. The copper oxide, cupric oxide starts to crystallize, which reduces the activity of catalyst. And this particular overall plant economy is actually dependent on the operating temperature, pressure, and recycling ratio. The CO2 is considered as carbon source for methanol rather than CO. Okay, so the CO is interconverted to CO2 through water gas shift reaction, and then 5 to 8% of CO2 in syngas which is actually required to initiate the methanol synthesis. So in the initial the syngas, the CO needs to be converted to CO2, and then this CO2 can actually act as a methanol synthesis reactor. Okay? So the overall reaction mechanism is so the both reactions proceed on the copper phase of the catalyst. The role of the zinc oxide is limited to the structure of the water in this particular reaction to the CO2. This is the water reaction, it gives the CO2 presence to then this particular mixture CO2 and the CO2 acts as the feed for the methanol synthesis is influenced with the methanol process. The dimethyl ether synthesis, it uses a dehydration catalyst like alumina along with copper zinc alumina based catalyst, and the properties uh, DMA. Dimethyl ether has a low auto ignition temperature, very high Cetane number, high oxygen content. The dimethyl ether suitable as fuel cells. It can also be used as additive to the biofuel to improve the emission characteristics. LPG substitute diesel engine like that. Okay. The different hydrogen production technologies, if you want to compare in this particular line, because when it's carry out this yellow reaction, uh, the hydrogen is also produced. We suppose when it carry out formation of the carry out the formation of the syngas. So in the product, there is apart from the carbon monoxide, there is oxygen and the hydrogen. Okay. So different kind of hydrogen production technologies include biomass reforming. Biomass is used as a feedstock, plasma cracking, hydrocarbon as a feedstock, uh, liquid phase reforming, thermolysis, electrolysis, photolysis. Different types of hydrogen production technologies are there. That is different efficiency and the maturities are shown here. Mm. So the overall block diagram of the as is shown here, the steam methane reforming produces the syngas, produces the syngas. So from the methane, from this particular steam, natural gas steam methane reforming, where there is a desulfurization unit. As I told earlier also, desulfurization unit should be there, and overall a cobalt molybdenum catalyst and zinc oxide bed and alumina guard should be there to convert this particular the pre reaction thing. And then the pre-SMR reaction, it's an adiabatic reaction on the nickel alumina catalyst 100 300 to 520 degrees Celsius, and then the steam methane reforming is on a nickel alumina catalyst with a particular energy content is there, and it undergoes again high temperature and low temperature, high temperature and low temperature on the shift reaction, so that the pressure swing adsorption forms the hydrogen. Then the methane decomposition, the another technique, where the methane can be converted into chemical species, carbon and hydrogen. So it requires some temperature because the endothermic nature of this particular reaction. So methane decomposition reaction enables direct production of hydrogen suitable for fuel cells or any other purpose free of carbon atoms. Methane decomposition requires only half of the energy that is required in the steam methane revolve. So it's much more energy efficient process. However, going to this particular high strength of hydrogen bond, this reaction unit temperature, high temperature around 1200 degrees Celsius in order to make it. So though theoretically it requires only half of its energy than it requires in a steam methane reforming reaction, but this particular carbon hydrogen bond in methane is so stable. Uh, um, so it requires about a very high temperature, about 1200 degrees Celsius. So overall, the methane decomposition having a different technological parts such as thermal cracking, athletic liquid cracking, plastic cracking, molten media cracking. In the thermal cracking, is thermal black process, advanced thermolysis, the cutting, having a metal catalyst cracking, carbon catalyst cracking, the plasma cracking having a plasma cracking having a thermal cracking electrochemical plasma. So there is a thermal plasma, there is electrochemical plasma, and also molten media cracking, which is having a thermal molten media cracking is molten media. So there is a thermal cracking of methane, as already shown here. Then the catalytic methane decomposition, the introduction of supported metal catalyst in to the thermal cracking of methane enables us to operate the cracking reactor around 500 degrees Celsius, which means that the hydrogen production more economically attractive. Different supported or powdered transition metals such as cobalt, iron, molybdenum, uh, nickel, copper, ruthenium, rhodium, platinum, rhenium, iridium, palladium, tungsten have been studied for metal catalytic nickel decomposition. Nickel or nickel alumina was found to be the most catalytically active species. However, the catalytic reactivation by carbon deposition over catalyst surface uh, into the pores of catalyst is still the major question. Then there is a plasma cracking. This particular methane, the methane cracking under high energy plasma has become an attractive method to produce uh, hydrogen in a single layer. Electronic method applied to generate plasma between the temperature difference between the electrons and heavy particles. Plasma technology is also classified into different types of things. the thermal plasma, there is a non-thermal plasma. Okay. Thermal plasma process gives an electric power of 1 kilowatt and the reactor attains a temperature of approximately 5 to 10,000 degrees Celsius. Thus, this process is a highly energy consuming process. The non-thermal process catalyzes the decomposition reaction at rather low temperature, at around 63 to 73 degrees Celsius, to the generation of extra species of first electrons. Molten salt media craft. The craft happens in the technical method leads to a bubble column reactor that is having molten salt, NaCl in air, molten metal like iron, tin. Advantages in removing the carbon species from the reaction zone. Differences. Densities of carbon black and molten media happens. So this is the basically advantage, and the carbon particles from the reaction zone can be actually easily removed uh, due to the density difference between the carbon black and the molten medium. Okay, so how it is very much important because it offers the opportunity to operate the hydrogen production reactor in continuous flow. Catalyst flux of reactor tubes due to carbon deposition can be avoided. The compatibility between the hydrogen, carbon, and molten media, the stability of molten media and various temperature ranges of the product might be the main source of difficulty for this process. And it is overall a nascent stage, so it is a partial process is under development. So with this, we come to the end of particular. But we'll then try to solve some of the sample assignment problems, which is the first question is that the what is the approximate percentage of world's energy consumption in terms of natural gas? It's 11%, 21%, 31%, or 40%. Correct answer is the 21%. The next question is that hydrocarbon dew point is a function of what are the parameters? Temperature, pressure, density, temperature, gas composition, density, pressure. Gas composition, pressure. So hydrocarbon dew point is a function of gas composition and pressure. Sure. What is A, B, and C? Okay, this particular application of the gaseous fuel for electricity production. So there are these options given. It's condenser, boiler, steam turbine, distillation, condenser, boiler, steam turbine, boiler, combustion chamber, steam turbine, distillation. Boiler and combustion chamber. So Air is boiler in the combustion chamber. Okay. Once the CNG undergoes the combustion, then it goes the gas turbine, the compressor, the alternator. Right. The gas turbine, the turbine exhaust goes to a boiler, and it produces the flue gases and the extra things. It goes to the steam turbine, and then exhaust steam cycle. Sun is produced, then it again goes to the boiler for steam generation. And from steam turbine, it goes to the alternator, and we get the electricity. It is supplied to the grid. Okay, so the steam turbine is the A, boiler in the B, combustion chamber is C, and the correct answers. The next question is that the two major components of syngas are methane and hydrogen, carbon dioxide and methane, carbon monoxide and hydrogen, carbon dioxide and hydrogen. Answer is that the carbon monoxide and hydrogen is the main components of syngas. In modern steam reforming process, catalyst used is nickel on ceramic support with or without promoter or stabilizers, iron-based catalyst, palladium, aluminum. These are the options. So, what is the modern steam reforming process catalyst is? It is a nickel on ceramic support with or without promoters or stabilizers. The reaction carried out in the reforming zone of autothermal reforming reactor is methane plus 2O2 gives CO2 plus 2H2O, methane plus H2O gives CO plus 3H2O, methane plus O2 gives CO2 plus H2O, or none of the above. Correct answer is the methane plus H2O gives CO plus 3H2. The H2O CO ratio in the autothermal reforming is around 4 to so 7. The H2O CO ratio in the autothermal reforming is around 4 to 5 or 7. The correct answer is the B. It's 20. So for low temperature pressure from synthesis process, written number of the product is nearly 20, 40, 60 or 80. Low temperature pressure from synthesis process, written number of the product is nearly 20, 40, 60 or 80. Current answer which what process is taken out other than hydrogen in the pressure swing adsorption rate? What product is taken out other than hydrogen in the pressure swing adsorption process? Syngas, tail gas, water gas, coal gas. Tail gas. The gas product uh, which is produced by steam from kilopascal has the following composition. It's nothing but to determine the partial pressure of each component. Is a mole fraction shown here. Hydrogen, H2O, CO, CO2, methane. So what would be the partial pressures? The total pressure is given. So the sim is a very simple thing. You have to just multiply the mole fraction into the total pressure. Okay, it would be giving you the mole fraction. 2100 multiplied by 0.392 would giving you the 823.2. Okay, 2100 multiplied by 0.392 would be giving you 823.2, which is first one, the hydrogen partial pressure. Similarly, 2100 multiplied by 0.438 will give you the H2O mole fraction, which is 919.8. Okay. Similar, it is very simple. Partial pressure will be total pressure into mole fraction. Very simple basic thing, Dalton's partial pressure. So this is all from my side. Anyone has any doubt, please ask. Otherwise, we'll discuss. Okay, no doubt. So we're ending the meeting here. Thank you.